Howdy and welcome. Advent Code 2022, day 23. Trying to get these done. Let's get started. Unstable diffusion. You enter a large crater of gray dirt where the grove is supposed to be. All around you, plants you imagine you were expected to be full of fruit are instead withered and broken. A large group of elves is formed in the middle of the grove. But this volcano has been dormant for months. Without ash, the fruit can't grow. You look up to see a massive snow-capped mountain towering above you. It's not like there are other active volcanoes here. We looked everywhere, but our scanners show active magma flows. It's got to be going somewhere. You finally notice the edge of the grove. You almost overflowing from random star fruit you've been collecting. Behind you, elephants and monkeys exploring the grove, looking concerned. Then the elephants recognize the ash cloud slowly spreading above your recent detour. Before any of them can form a complete question, another elf speaks up. Okay, new plan. We almost have enough fruit, and the ash from the plume should be spread here eventually. If we quickly plant new seedlings now, we can still make it to the extraction point. Spread out. The elves reach into their pack and pull out a tiny plant. The plants rely on important nutrients from the ash, so they can't be planted too close together. There isn't enough time to let the elves figure out where to plant the seedlings themselves. You quickly scan the grove and note their positions. For example, the scan shows elves pound and empty ground dot. Outside your scan, more empty ground extends a long way in every direction. The scan is oriented so that north is up. Orthogonal directions are written north, south, east, west, and east. All diagonal directions northeast, northwest, southeast, southwest. Elves follow a time-consuming process to figure out where they should each go. You can speed up this process considerably. The process consists of some number of rounds during which the elves alternate between considering where to move and actually moving. During the first half of each round, each elf considers 8 positions adjacent to themselves. If no elves are in those 8 positions, the elf does not do anything. Otherwise, the elf looks in each of the 4 directions in the following order and proposes moving 1 step in the first valid direction. So, looks in those 3 directions, north, northeast, northwest, and moves north if there's no elf. Okay, then south, then west, then east, okay? After each elf has had a chance to propose a move, the second half of the round begins. Simultaneously, each elf moves to their proposed destination tile if they were the only elf to propose moving to that position. If 2 or more elves propose moving to the same position, none of those elves move. Finally, at the end of the round, the first direction the elves considered is moved to the end of the list of directions. For example, during the second round, the elves would try proposing a move to the south first. Then what? Okay, so those loop. Okay. Northernmost 2 elves and southernmost 2 elves propose moving north, while the middle elf cannot move north and propose moving south. Everybody moves except for these 2 because they both propose moving to the same location. All right. Then, okay, so, all right. Okay. So this is another like infinite graph problem, sort of like or that growth thing, Game of Life. I forget whose name is associated with that, but like things can grow and they have rounds and it can grow out infinitely. So we need to. So I would suggest that we don't use a like a map. I suggest that we actually just use like sort of a sparse map, some sort of position tracking. To make sure they're on the right track, the elves like to check after round 10 that they're making good progress toward covering enough ground. To do this, they count the number of empty ground tiles contained by the smallest rectangle that contains every elf. Yep. In this region, the number of empty ground tiles is 110. Simulate the elves process and finally find the smallest rectangle that contains the elves after 10 rounds. How many empty ground tiles? So yeah, obviously I think part 2 is going to be simulate after like, a million rounds or something like that. But let's just implement the 10 rounds. But one thing I learned from doing yesterday and thinking about last year is that we need to check the puzzle input. This doesn't seem too different from the example, which is good, but it has many, many more. Whoops, day 23, input. All right. All right, let's read it in. Start going. So no. We don't want to do that. We just want to do, well, yeah. So what we're going to do is just lines with strings. So we're not even going to modify the input. We're just going to read it in as is. And then for part 1, we're going to do a sparse mapping. So we're going to get the position of every single elf. So all right, so our part 1 state, we're just going to have elves, which is a set of location. Yep, and that's it. And then the other state is the iteration count. Yep. Cool. So, and then the directions. Nice. Okay, so first we get a state equals state of input. And input. And so self.elves equals set of I location ij for I in range len of input for j in range len of input input.lines I if input dot lines I j is equal to pound. Then we have our elf locations, and all right, so that's that. Good. Then we are ready to start our state. So we just need to do 10 rounds, right? For round in range 10. So we need to calculate empty ground tiles, and we need to do a like an iteration. So yeah, I guess we'll just call this state. That's fine. So then def round, execute round, or we'll just call it iterate, self, pass, and then we also need def empty ground tiles. So the empty ground tiles is pretty easy. We just get the minimum row and column and then subtract the total number of elves from the area of that. So height equals max e dot row for e in self dot elves minus min e dot row for e in self dot elves. And I believe we have to add 1 here. So if you go from so if we start at the beginning here, so this would be 1, 2, 3, 4, but we want height 4 and 4 minus 1 is 3. So we have to add 1. We'll do the same with width. And then we return height times width minus len of L self.elves. And that is the empty ground tiles, right? So right, and then state.iterate. Cool. So first half of the round is for elf. For each elf, we need a location. So we map their current location to where they want to go. So elf desires is a list of tuple of location to location, where they're currently at to where they want to go, equals elf, and then self.desired or propose move elf, and then we give it an iteration number, which is already there, right? So we already have the, right? And then, so that'll give us the proposals, def propose move self elf location, gives the location. All right, then we have for direction, for in range 4, direction equals direction of dir I plus self dot iteration mod 4. So this will allow us to, go north, south, east, west, east, right? That's the order. North, south, west, east. But then when we iterate once and we have iteration 1, then we'd start south, west, east, north, right? And so this will do that. And then if direction equals direction dot north, then we have to check north, northeast, northwest. So if location so we need to go 1 row up. And we're just going to set the checks and the proposal direction for each of the 4 directions. South, we do elf row +1. West, we go elf row plus I, and elf call. West would be -1. +1 plus I. East. If all, oh, right, we got to do elifs here. If all check not in set, not in self.elves, for check in checks, return checks 1. Right, 1 is the middle of these 3 checks. So we, right, so that would be south, west, northeast, right? And then moving one step in the first valid direct, if, we also have to check if there are no elves in any position. So So basically this will check +1 0, +1 1, +0 1, +1 -1. This will check all those locations except for the position right where you are. And so these are our no move checks. And if all check not in self.elves, for check in checks, return elf, right? So if you're not moving, then you just return your current location. So if, right? So this is the don't do anything. Otherwise move in the first valid direction. I suppose everything's guaranteed to have a valid direction. I suppose just in case, if we exit this, we'll just return elf, right? Like if there is no valid direction in the 4 valid directions, then you just return where you are. Okay. All right. So now we have the proposals, and proposal set equals proposal for proposal in proposals. So we just get a set of that, and then we do new elves equals current proposed if proposed. We need a count, right? We need a frequency count. So let's make a little frequency set. List So a little frequencies. So let's make this frequency frex of all right. So we want to take the proposed if the if proposal of the proposed is equal to 1, else current for current proposed in proposals. Right? Then we do self.elves return state self.elves equals new elves self.iteration plus equals 1. All right. So now we have new elf positions. Cool. And then let's make a print. So okay, now we have a print, so we can just do all right. Wait. So this is saying that it couldn't find a proposal in the proposal frequencies. Ah, yes. Okay, cool. So when we begin, we have 4, 0, row 0, 4. That's not true. Oh, yeah. Row 0, 4, 4, 0. Yeah, those are all elves. Okay. Then, okay. All right, they did move. We're just not drawing it correctly. Left is the minimum column, right is the maximum column. Bottom is the oh. All right, 110. That's correct. Okay. All right. Let's remove this print and run it on the input. 4254, try the answer. That's correct. Nice. All right, we just implemented it as it was. Let's get to the more difficult problem. It seems you're on the right track. Finish simulating the process. Figure out where the elves need to go. How many rounds did you save them? For example, the first round where no elf has moved is round 20. Fine. All right, so now we need to know when no elf moves. How can we do that? We can have iterate return a Boolean. So no elf move doesn't mean they all propose not to move. So it could mean that they just actually didn't move. So it's just a question of whether new elves is equivalent to self.elves, right? It's like, because you can't switch locations. So it's, if the sets are equal, then there's no move. $20 is correct. Let's see how long this takes for part one for the input. I think it could go for a while. 992. Hey, we got it right. Nice. So, I mean, I think obviously the key here is the sparse nature of how we stored the state by keeping a set of locations rather than a map. Like it's very tempting to want to make like a big matrix, but because it can keep growing ad infinitum, like that can get really tedious. And nothing here was too difficult. You know, instead of checking where we are in a map, we check where we are in a set. So I think this was pretty good. Hope you guys enjoyed this one, and I'll see you for the next one. Peace.